It gives me great pleasure to introduce the opening plenary speaker for this conference. It's Mark Harrison. Mark started his career with a bachelor's at UBC, PhD at ANU, postdoc at Carnegie, and sunny Albany. But he's spent the majority of his career at UCLA for the last 20 years. He had a brief break where he's director of the Earth Science Institute at ANU, came back and is now director of the Institute of Geophysics and Planetary Physics. He's won numerous awards and medals for his contribution to science. Most recently, he's just been awarded the Days Medal, one of the most prestigious medals from the GSA. And it's a great pleasure to introduce Mark's talk, which is titled Probing the Dark Earth, Crust-Water Interaction on the Hadean Earth. Mark.
Thanks very much. It's a tremendous honor, hard to describe just how honored I feel to have been asked to give this opening talk. And with that sense of honor, clearly a sense of responsibility, so much so that I gave what is essentially a dry run of this talk last month at a meeting in Toronto. After the talk, my wife called at lunch, asked how it had gone, and I said, well, look, I'll just pass the phone to somebody who was in the audience, to a trusted and dear friend, who said, Sue, about the best thing I can say about Mark's talk is that he recovered well from his failed attempts at humor. And which was really no surprise to me, because in 26 years of coming to international meetings, I had in fact inspired my first heckler, who in fact, a lady in the front row who had said, if you want us to laugh, could you give us some sort of indication you're about to say something funny? So, rather than learn my lesson, can I suggest that when I raise my left hand, that any chuckle or titter would be appreciated. Thanks. Anyway, I'm here this morning to talk over this noise in the back. Essentially talk about origin myths. My own and others. Origin myths are so common in human society that it seems that our species is hardwired to create explanations, even when faced with things that are unknowable. Indeed, if our species has been roaming this planet for over 100,000 years, it's hard to imagine that they haven't been speculating all that time on the conditions and when the planet formed. If you Google creation myths, there's a number of sites that have thumbnail sketches of a large number of creation myths. You read a dozen or two and you start to see some common threads. For example, an egg-like feature emerging from some kind of vegetable is not uncommon. The so-called water diver flood myth that the Judeo-Christian tradition adopted with gusto is also common, not just to Judeo-Christian, but the Iroquois, the Japanese Aboriginals, and so on. When you relate specific myths to a culture, I think you start to see that the fundamental controls on origin myths are the limitation of the historical record, the level of technology, and of course the what vegetables you have at hand, because of course the universe isn't going to emerge from a gigantic rutabaga if no one's ever seen one before. Thank you. Well, despite our impressive technology and perhaps the Western cultural bias towards a watery origin, when it came time for the scientific community to confront its limitation of the historical record, there's simply no rocks known older than about 4 billion years, it chose a paradigm of a desiccated continent-free wasteland in which rock formation at the Earth's surface is largely due to a collision with space debris. And it called it the Hadean era, the hellish time. Well, here's a timeline showing sort of major milestones in the evolution of life on the planet. Here's the Hadean, the first roughly 500 million years of Earth history, and certainly this was the most geodynamically vigorous time in the planet's history. During this period, it's variously speculated that we encountered a Mars-sized object forming the moon, that we had a magma ocean or magma oceans created, similar to proposed for the moon, and perhaps even that life had emerged in this time. And what's really most interesting is the one thing that these three hypotheses have in common is there's absolutely not a scintilla of geochemical evidence that requires that any of them happened. And of course, that's because there is no rock record older than 4 billion years. That hasn't stopped us, however, from speculating on the nature of very early Earth. And I think the paradigm for the past few decades is well embodied by this, this illustration, showing the kind of an artist's conception of early Earth, or in fact embodied in this text here from the, I think otherwise very good book, Rare Earth by Warden Brownlee, suggesting that for hundreds of millions of years after Earth formation, there was no water at the surface, and indeed temperatures high enough to, in fact, have a continuously molten surface. The story that is emerging from the Hadean zircons I'm here to tell you this morning is somewhat at odds with this paradigm. And what are these Hadean zircons? Well, there are numerous localities on the planet now. There's Hadean zircons, zircons older than 4 billion years, known from southwest Greenland, from northern Canada, various locations in Western Australia. The grains I'm going to talk to you about come from this part of the Yilgarn Craton in West Australia, the Jack Hills, a small portion of which shown here. The zircons are in these pebble conglomerates like this. A small fraction of the rock is zircon, about 100 parts per million or so typically. And of the zircons in the rock, only about 3% are older than 4 billion years, and only 3 per mil older than 4.2. So if we want to make stories about the early Earth, the Hadean Earth, I think we've really, the only things we got going for us, we can assume physical laws are constant and that radioactivity was, say, 3 or 4 times higher than it is today, that the solar system hadn't yet cleaned itself up, and that there was high impact flux, and then we've got the Hadean zircons. When we look at these, we see evidence of widespread water. We see evidence of early differentiation of the silicate Earth, and even a suggestion that the magmatism, for which the zircons represent, formed in a surprisingly low heat flow environment, and this we interpret for evidence of an early hydrosphere, early continental crust, and even possibly plate boundary interactions. Okay, well, let's talk a bit about zircon. Zircon is obviously zirconium silicate. Zirconium, silicon, and oxygen. You can see 2/3 of the mineral's oxygen, so there's every expectation that we'll be able to do precise and accurate stable isotope measurements of oxygen. But like every other mineral under the sun, it's got every element under the sun. It particularly likes heavy rare earths, loves hafnium, talk a bit about that later, likes thorium, uranium, and even plutonium, which was hanging around the early solar system. And even some elements that it doesn't much like titanium, in fact, also have opinions about the nature of water on early Earth. So because of this strong enrichment in thorium and uranium and the fact that the mineral almost completely excludes lead, we have a great chronometer. We can use uranium and thorium decay by alpha and beta processes to isotopes of lead. And we use a device called a high-resolution ion microprobe, or secondary ion mass spectrometer. To date these things, we point a very narrow beam, about 1/4 the width of one of the hairs on your head, onto these old zircons, or the candidate zircons. This causes secondary ions to be sputtered, removed from the surface, and put into this big mass spectrometer. So almost non-destructively, we can accurately, precisely determine the age of these zircons. And this is how we're aware that only about 3% of the population in Jack Hills is over 4 billion years. There's been a mammoth effort, and I acknowledge the fantastic efforts of colleagues at the Australian National University and UCLA because over the past 8 years, we've age characterized 150,000 zircons from the Jack Hills in order to identify about 5,000 grains that are between 4 and almost 4.4 billion years old. And I mentioned we'll come back and talk about lutetium hafnium a little later. Well, how can an anhydrous phase tell us about water on early Earth? Briefly, 4 ways at least. We see evidence of an enriched oxygen 18 in some, suggest that there were clays in the protolith, magmas that form the zircons, and this implies water at or near the Earth's surface. The zircon formation temperatures cluster close to that of wet minimum melting. The inclusions themselves indicate hydrous magmas of both sort of S and I type. And lastly, more speculatively, that the varying plutonium uranium that we're able to infer from fission xenon studies suggest the water as the mediating solvent for that fractionation. So back to oxygen isotopes. This is 8 years ago, 2 groups, us and a group from West Australia and Wisconsin, simultaneously recognized that relative to the Earth's mantle, here represented by lunar zircons, the oxygen isotope, the isotope of oxygen 18, was enriched in a fraction of these zircons. See this population pulled to the right here, including values that were characteristic of samples or materials that had been through a sedimentary processing involving clays, enriching the protolith in oxygen 18. As shown here, here's a case of a clay at relatively low ambient temperature and a very strong fractionation for oxygen 18. Although not a unique explanation, both groups independently suggested that this was evidence that there was water at or near the surface of the Earth prior to 4.3 billion years. More recently, the advent of the titanium thermometer for zircons. You can see here the concentration of titanium in a zircon, in this case buffered the presence of rutile, is a simple function of temperature. For example, a zircon with 10 ppm titanium, in this case, would crystallize, let's say, at about 720 degrees, something like that. So by measuring the titanium concentration in these old zircons, here's a 4.2 billion year zircon. You can see the cathodoluminescence showing these sort of tree ring-like growth zones in the zircon. Here's the core and the rim, and you can see the zircon cooling from, say, 780 to 750 degrees. The big surprise to us was the large number, measuring a large number of these Hadean zircons, over 300 by now, produced a relatively tight distribution, this single kind of Gaussian, at a temperature of about 680 degrees. And although there were observations of temperatures slightly higher than that, subsequently we learned that this was contamination. Well, this is very close to temperatures that would be associated with virtually water-saturated melting of felsic materials, 680 degrees, say, requiring 15 or 20% water in the magma to achieve such low temperatures. And this was our initial interpretation, which really seems to have been borne out to subsequent studies. Although zircon is not, it's characteristic of the crust, it's not unique to the crust. There's zircons on the moon, zircons in meteorites, zircons from the mantle, but the temperature distribution of the Hadean zircon seems distinctive from, say, that of mafic zircons produced by the Wisconsin group, certainly distinctive from lunar zircons. And the geochemistry of the Hadean zircons distinctive from, say, Morib zircons or other sources from the mantle. Now, there's some overlap between the Hadean population and mafic zircons, and if there's some selection mechanism, say that preferentially concentrates low-temperature zircons, say from mafic sources, it could be possible to generate that distribution. Now, there is a preservation selectivity, but in fact it works in the opposite direction. It's possible that this Hadean population may underestimate the number of low-temperature zircons, because now that we've got a zircon thermometer, we can tell the temperature at which these things formed. We find what we long suspected, and that is that it's the low-temperature zircons that have the highest uranium concentrations, and it's these zircons here that are going to be most susceptible to radiation damage, to becoming metamict, and essentially, committing suicide in the process of being transported to a site of deposition of tetraidal zircons. And indeed, we don't see these sorts of high uranium concentrations in the Jack Hills population. And lastly, as I mentioned, some sort of anomalously high temperatures that we initially saw when we developed this process of titanium ion imaging. You can see here's a zircon with a crack in it. It's got 5-6 ppm. This corresponds to a temperature of around 690 degrees or so. But if the beam hits these contaminated regions here, anomalous results occur, and we were able to separate these results and further solidifying this sort of Gaussian bullet at about 680 degrees. Okay, the mineral inclusions, every zircon we've looked at has inclusions in it. Here's a zircon with, again, you can see the nice cathodoluminescence imaging. This has got a inclusion of biotite, sphene, and hornblende and graphite. There's another population, another kind of assemblage of, say, feldspar, muscovite, quartz, monazite, that are characteristic of perluminous melts. So we see sort of both types of convergent margin magmatism. Diamonds have been reported. We have not ourselves seen the diamonds, but perhaps suggesting ultra-high pressure metamorphism. Now, the hornblende and the muscovite, they're amenable to barometric methods. In both cases, we see pressures of 7 kilobars or somewhat higher. Here you're looking at data from the Fengite barometer in muscovites. We've looked at temperature, again, around 700 degrees, pressures of around 7 kilobars. So this corresponds to an apparent geotherm where these granitoids formed, and the zircons, for the most part, to say characterized by granitoid mineral inclusions, of about, say, 30 degrees per kilometer. Now, pick any thermal conductivity you want, and that's going to translate to a heat flow of something like 75 milliwatts per square meter, and that's remarkable only in that that's just about the average value of global heat flow from the planet today. But wait a minute, 4.3 billion years ago, surely heat flow was substantially higher. Most models would have it 3 or 4 or maybe 5 times higher globally. So of course there are places on the planet today that have heat flow 1/3 or 1/4 of the global average. The Canadian Shield's one example, but the only place on the planet today that you make magmas in a region characteristic of 1/3 the global average geotherm is in subduction zones, where of course the oceanic lithosphere is refrigerating, it's subducting and refrigerating the overlying plate and producing magmas with this characteristic thermal signature. So we take this as perhaps evidence of some kind of, well, certainly of underthrusting and some kind of plate boundary interaction, possibly akin to modern subduction. Okay, more speculatively, as I mentioned, we've undertaken studies of fission xenon with our colleagues Grenville Turner, Jamie Gilmore at University of Manchester, and their transcendental mass spectrometer RELAX, which is capable of making percent level xenon measurements on tens of thousands of atoms. And I'm more or less sure that you folks haven't seen a diagram like this, because I don't think it existed before Grenville invented it recently. And what you're seeing is a plot of xenon isotopes, 3-isotope plot of xenon, showing you where, in fact, spontaneous fission of uranium occurs. What's the, every time a fission track is made, on average, that's the 131, 134, 131, 132, 134, 131, 134 composition. This is where pure plutonium-244 plots, and of course, we're aware from meteoritic studies that there was a fair bit of this hanging around in the early solar system, about 1 part for every 100 of uranium at that time. But the half-life of 82 million years is such that by the time the rock record cuts in at 4 billion years, plutonium-244 is essentially extinct. But these old zircons should have a record. In addition, we've irradiated these zircons, artifactually produced fission xenon from 235 irradiation, such that as you move up this axis, you're going from 0 plutonium uranium to infinite plutonium uranium. Along here, from 0 age to infinite age, in terms of the xenon retention. This is the uranium xenon retention age. And then if you've lost xenon, you could pretty much have any trajectory in this field here. Now, this stippled region here shows you the range of plutonium uranium that we've seen and the ages of samples we've analyzed between about 3.9 and 4.2. So any data that plots here, okay, we're pretty confident hasn't lost any fission xenon. The data, in fact, largely have lost xenon in the course of their history, and those data are shown with the white circles, the core. But about a third of the data are within uncertainty of being concordant. That is, the uranium xenon age, the xenon retention age, is within uncertainty of the lead-lead crystallization age. Okay, so the remarkable thing is, at least in this preliminary result, we see plutonium-uranium ratios varying from essentially, chondritic down to 0. So how do you separate uranium from plutonium? Well, we don't think that it's likely to be done magmatically. We don't know everything there is to know about plutonium's behavior in silicate melts, but what we do know suggests that it would be difficult to completely fractionate these phases magmatically. However, plutonium, all species of plutonium, 3 through 7, and if you've never seen them in solution, here's your opportunity. For various reasons, these are highly insoluble under, say, most conditions we could imagine for the Hadean. Likewise, uranium plus 4, relatively insoluble, but under appropriate redox conditions, uranium plus 6 would have very strongly contrasting behavior. So the preliminary interpretation is that water is the likely solvent that would separate plutonium from uranium, and indeed, so even in the presence of low oxygen gases, Dmitry Sujensky was kind enough to run some calculations for us and show that when we say oxidizing FO2s of order 10 to the minus 50, or in certain circumstances high enough to create the uranyl ion. So we're not really talking about needing sort of modern atmospheric oxygen to affect this. Okay, moving on, I mentioned lutetium hafnium, lutetium-176, beta decays to hafnium-176 with a half-life of 37 billion years. That's a long time, such that if you plot, here's the daughter over a stable isotope of hafnium as a function of time. Here's the beginning of the solar system, say 4.57 billion years. There's essentially a linear growth, the bulk Earth, of hafnium-176 relative to 177. What you're seeing here is a two-dimensional probability density function of a large number of 250 hafnium isotope analysis of these ancient zircons. And my point here is to say, if we take model ages for these data, we see in the simple model the suggestion that the protolith of these zircons, in fact, began forming almost immediately upon Earth accretion, 4.5 billion years, and was relatively constant through time. Mind you, these are model ages. What's, I think, the icing on the cake here is that there are 5 data that plot down here when adjacent what is essentially the forbidden zone. This is the initial hafnium-176-177 ratio of the solar system, and yet at 4.3 all the way down to 4.0 billion years, we have zircons that plot essentially within uncertainty, or within an epsilon or so of the solar system initial ratio. Now, these protoliths of these zircons are going to have to remove themselves from, bulk Earth, lutetium hafnium, in order not to grow any radiogenic hafnium. Here's one case. It's in fact this grain right here. We'll take a closer look. Here's the zircon. There's a core and a rim relationship. The core we've dated by using the ion probe, age of 4.32 billion years. Then we drilled a big hole in this with a laser and simultaneously analyzed hafnium isotopes to get the hafnium isotope composition, the 176-177 ratio, and looked at the lead-lead age all the way down this big hole. And in fact, I think we're confident that this zircon core is 4.32 billion years, and yet it yields a hafnium composition which is essentially identical with the initial ratio of the solar system. So even if this zircon formed in a zero lutetium-hafnium environment, it has to, the protolith, the precursor material, has to have been removed from the bulk of silicate as early as about 4.51 billion years. There's 5 of these very non-radiogenic zircons. Our statistical tests suggest that this is, these are not, 4 sigma outliers, that this is real information, and thus requires, I think, that any model of, say, Mars-sized impactor forming the moon, of core formation, of magma ocean on the planet, that this all has to be over with by 4.5 billion years. Okay, just summarize. A successful model to put all this together needs to explain the zircons that are oxygen enriched, the low crystallization temperatures, and if I didn't mention, surprisingly, 2/3 of all inclusions in the zircons are muscovite and quartz, on roughly equal abundance. The very primitive hafnium isotopes of many and some extremely primitive ratios of a few of the grains, the apparent crystallization under a surprisingly low geotherm, again more speculatively the fractionation of plutonium from uranium, the continental-like trace element signatures, and these 2 characteristic inclusion assemblages that look like, say, per-aluminous, metaluminous assemblages. Let me begin by wrapping up by showing you models we don't think work. Obviously, there was probably a lot of, say, cleaning up of the solar system to do back then, and it's tempting to imagine that the melt sheets that would be formed upon these impacts, of course, they're eventually going to crystallize zircon. There's zirconium in virtually every rock. But these melts are going to be typically dry. Even if you vaporize the entire ocean and produced a steam atmosphere of 270 bars, you're not going to get the solidus down much below 800 degrees. So we think that the temperatures are too high. And actually, if you take a global database of analyzed rocks and their zirconium content, the median temperature of a zircon formed by just randomly hitting some part of the present Earth would be about 800 degrees, much higher than the Hadean population. And indeed, when we look at modern melt sheets, for example, we have materials from Sudbury, Vredefort, and Morakwang. The temperature distribution actually mimics the mafic zircon distribution more than it does the Hadean, and indeed, the median temperature is close to our global calculations, so we don't think that's likely. I've mentioned I don't think it's plausible that the zircons come from mafic sources. I've already mentioned some of the reasons, the trace element signatures, it's possible in certain circumstances to create the heavy oxygen, but I don't think it's a robust explanation, not likely to produce muscovite inclusions and so on. Since the advent of our barometric measurements suggesting this crystallization, this low geotherm, a popular response was that, well, look, you don't need subduction, you just need a cold downwelling. But I think it's unlikely either in the case of the case where you actually did have some sedimentary processing at the surface or a sinking eclogite. There's at 20, 30 kilometers going to be very little pore space, very little molecular water to enhance melting. The water that's released as a result of dehydration reactions as the downwelling proceeds is likely then to ascend and rehydrate rocks at shallower depths. And certainly in the case of a sinking mafic eclogite, we're unlikely to to create a situation which muscovite is the dominant inclusion phase. Seems more likely that these would be produced by introducing water, lots of water, to rocks at about 700 degrees that were fertile for the different sorts of melt chemistries that we infer from the inclusion mineralogy. So it's hard to say anything particularly concrete about a time in Earth history that's not represented by the rock record, but I think we can draw some reasonable inferences from the data that we've obtained thus far. And I think the first is, frankly, the simplest explanation for everything we see is that the planet was behaving a lot more like it does today than we've previously thought. That the silicate Earth had, in fact, differentiated early, and this is, of course, supported by neodymium isotope results. That mature sedimentary system was active, producing or contributing towards these contrasting melt chemistries. That this cycling likely involved underthrusting, possibly similar to modern subduction, but because of the active nature of this recycling process, that by 3.8 billion years or so, most evidence of this early crustal activity was erased. And call out Beth Ann Bell's talk this Thursday, where she's in fact looked at zircons from the Jack Hills population younger than 4 billion years, and can make some more specific, find more specific constraints on the time scale of recycling. This is here just to remind me to say that it wasn't that long ago that the conventional wisdom was that you couldn't have plate tectonic-like behavior in the Hadean. It was ruled out by these various lines of evidence. But to point out in the relatively recent past, just the last 4 or 5 years, that what we used to think of as sort of kind of concrete rules have been transcended by, for example, the recognition, the possibility that there was a high degree of mantle depletion prior to 4.5 billion years. So I won't dwell on this, and in fact, I'm going to leave you with this slide here showing our speculative views of possibly in a very different first 500 or 600 million years of Earth history, and I hope there's questions. Thanks very much.